All right, guys. Finish that last one. You should be done with that last one. Go ahead and write down what's on the board for me, okay? Finish it. I'm going to need to finish your concept, but I want you to teach me. Leave some space. Next part of our notes. I need about 20 minutes to finish this up. I'll pass the back around and take what you need. So I'm pretty sure my dog is going to scare them all away. He does not like visitors. He loves visitors when they're in the house, but outside the house, he's like, alert, alert, danger. Okay, so as you're writing down what's up here, it's very familiar. We just did this, but we did it with a very simplistic example where the data was given to you, like, mass was given to you, C was given to you, delta C was given to you. So this example just kind of repeats what we were just doing, but it's solving for a different variable. And then we're going to talk about calorimetry and how we can bring this together with another substance. Okay. So this is actually a question from your problem set, which is, if you looked at the work energy problem set, right next door was the heat transfer problem set. Do you guys see that? Yes? Okay, I'm doing number 4 with you, okay? If I can do all of them with you, you don't have to do them. Okay, so let's work. All right, so go ahead and tell me, looking at the variables, and this is how I would always imagine that you would do this for yourself. Write down the variables and write down the quantities given. So what's the first thing we're given? Mass is 95.4 grams, and this is a piece of copper, okay? And it tells us what else? Delta T, which is T final minus T initial. Don't forget to always do that. What's T final? 48 degrees Celsius. And then 25 degrees Celsius. So what's our delta T? 23.0 degrees Celsius. Don't forget, sometimes you gotta pay attention to those decimals. All right, so there's our delta T. What else is given to us? The heat, right, which is what? Q. So Q is 849 joules. All right, so what are we solving for? Solving for what variable? C, which is specific heat capacity, which has what units? Joules over grams degrees Celsius, right? So it should be a complex unit at the end, so let's verify that. So let's take all of this, plug this into Q equals MCAT, which is internal energy. Solve for what? And then how do I solve for C though? What's my variable? What are my variables? Q over MAT, the M delta T. Okay? So Q over M delta T. All right, so Q is 849 joules. Make sure you write your units. Divided by, what's my mass? 95.4 grams. That multiplied by 23.0 degrees Celsius. Okay, before we calculate, what units cancel? None of them. What's the point, right? Because it shouldn't cancel because this is C. All right, and then calculate for me. I'm going to actually calculate these. Point what? 3. How many sig figs do I need? How many? 333, right? So I need 3 sig figs. So then what is the answer? 3.8 or 0.387 joules per gram degree C. Beautiful. And note to self, metals have small C's, okay? That means that, actually, let me let you rationalize this first. Can you guys describe what this means to the person next to you? What does this C value even mean? Okay, come back to me. Come back to me. Who can verbalize what this means in like 10 seconds? Who? Volunteer Chase? Okay, thank you.
So the amount of energy takes to raise, so 1 gram of substance does 1 degree Celsius.
Okay, so this is copper, right? So it only requires a smidgen of energy, like a third of a joule, right? 0.387 joules to raise 1 gram of copper by 1 degree Celsius, because these are imaginary ones, right? So it takes basically nothing. So copper's going to heat up real fast, right? What has a high specific heat capacity? Water, which is what? 4.18 joules per gram degree C. So how much energy does it take to raise 1 gram of water by 1 degree Celsius? A heck of a lot more, like over 10 times more, right? So that's why water is not going to heat up so fast that, let's say, the ocean, it's got the big sun on top, it's glaring down on it. You can still go in the ocean after a day of thermal energy being delivered to it, because the water's still going to take a lot of energy in, but the temperature doesn't reflect that. The temperature warms up a little bit, but not a lot of it. Okay? So this is going to heat up really fast. Okay. The next style question is transfer of energy. That first one was just internal energy, like what does this one substance have if it changed a certain temperature. This is the transfer of energy between two objects in the system and the surroundings. So this is the one that combines two cubical symptoms. I always have grandiose plans, like we're going to get through everything in one day. This doesn't happen. So just put a timer on myself, because I know I'm not going to finish. Calorimetry. That one? System. It's called system. I'm just joking. I correct myself sometimes. My husband tells me I'm not funny, but it's what it is. He laughs inside. I told him to make me feel better. He's laughed outside too, but he doesn't. Okay, so who remembers setting Q equal to Q in honors chem? Oh, William. Okay, very few of us. Okay, so the idea is that the law of conservation of energy exists. So the energy lost or transferred from one system is gained by the other system or the other part of the system. So many times, though, we do specify like one object and another object, like a piece of metal and then water, or a system and a surrounding. But both of them can gain, so one has to be negative, one has to be positive because of the nature of how transfer occurs. So it does relate back to the first law of thermodynamics, LDTD, first law of thermodynamics, and we are measuring the heat change, the heat meaning joules change as a process is occurring. So this will make more sense when I do an example, okay? So what this system and surroundings actually means is MCAT, so MC delta T of the system is set equivalent to the MCAT of the surroundings. And let's say the energy of the surroundings went up. Does that mean it's an endo or exothermic process in reference to the surroundings? Sorry, in reference to the surroundings. If the energy of the surroundings went up, this one what? Endo, it gained energy, but the system released energy, so it's the negative. Okay, so you do have to read it carefully. Okay, so as you read this, first, describe who's the system and who's the surroundings. Blah, 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 blah was the first thing that sticks out to you. Metal, okay, so metal is one subject. What's the other thing? Water, okay, so whenever I write my variables out, it's a little overkill at first, but then work with it because it will make more sense. Put metal and water and make a little table. Okay, as you read, what's the first thing it's asking for? C of what? Of the metal, right? So that's my question. What is the next thing it gives you? Mass of a metal, so M is 50.00 grams. Blah, 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 blah. Raises 100 milliliters of water. Okay, so that is not volume, because notice in MCAT there's no V's. So what is that really trying to deliver to us? Mass of water, because 100 milliliters of water is equivalent to 100 grams, so 1 gram is equal to 1 milliliter, right? So just for water, okay? So mass is 100.0 grams of water. And a calorimeter, so we'll deal with calorimetry a little bit more, and it's raising the water from 34 degrees Celsius to 36 degrees Celsius. So who is that talking about? Water, right? So the delta T for water is TF minus TI. So it's what minus what? 36 minus 34, so the change is 2 degrees Celsius, 2.0, right? Yeah, so 2.0. And then The initial temperature of the metal is 95 degrees Celsius. The final temperature of the water and the metal is 36 degrees Celsius. I'm going to call that 95.0, just so I can keep my secrets there, okay? You can't change questions, but I can, okay? So what's my delta T? 36.0 minus what? 95.0. So what's that? Negative 59.0 degrees Celsius. Okay, what's the only variable that we're missing? C for water, right? But we actually know what that is. What is it? 4.18 joules per gram degree Celsius. Or you can call it 1 calorie, because 1 calorie is equal to 4.184 joules, remember? You could decide this to be calories just as well as joules, because it doesn't specify which one, so either one would work for me. So we're going to take all this information, but really we're just going to set Q equal to Q, because MCAT is here, this equals AQ, and MCAT is here, this equals AQ. Which one is losing energy? The metal gets the negative, right? Who's gaining energy? The water, and you can see that by nature because the temperature is increasing. So technically what we're doing is we're setting Q of metal equal to Q of water, where the water gained energy and the metal released energy. That's technically what we're doing. But I don't really have Q. I could actually calculate Q myself over here and then plug it in, but many times I just plug in all the variables and let's go with the flow. This is equal to negative MC delta T, but for metal. So little m next to it is just me saying metal. That's equivalent to equal to MC delta T for water. Which variable am I solving for of these six? The C of metal, right? I'm solving for that C right there. So tell me variable-wise, when you rearrange your equation, what is C equivalent to? MC delta T of water, because that's all this over here. MC delta T of water divided by negative, right? The negative comes with us, negative what? M delta T of metal. Plug, 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 solve. Plug everything in, solve. Just make sure I'm videoing. Yeah, okay, good. Alright, so you'll notice that we have a small value again. Does this make sense for the metal? Yes, because metals are really conductive to thermal energy, so they heat up quite fast. Therefore, they have a small specific heat capacity. And then we had 2 sig figs from the 2.0, so it should be 0.28 joules per gram degree Celsius. Okay? Thumbs up when I can move on. Okay, so I'm kind of doing one of each type. This was number 2 or something like that, or number 1 on your problem set, maybe. You guys can verify that. All right, so I've got just a little bit more I'll do today. This takes minutes, so go ahead and read, write, and then I'll talk. This is a little different than specific heat capacity. This is just simply heat capacity. Notice there's some difference here. So the word calorimetry is just still talking about transfer of heat and the process of actually calculating that transfer of heat or accounting for another variable in that process. So calorimetry can be applied to many situations. So this other form of calorimetry, which actually relates to the container or the object that you're maybe measuring temperature in, we actually can calculate the heat that object absorbed. So if you have a cup or a coffee cup or a beaker, that's a piece of the surroundings. But the surroundings themselves can really do some damage to our calculations because they themselves can absorb energy. What's a great insulator that doesn't absorb any energy? So what would you get it at the gas station? Say again? It's a cup and it's foamy. Styrofoam, right? Styrofoam is what we generally use. I thought somebody was saying it, but then you weren't, so okay. Oh, sorry. Well, I mean, where else do you get styrofoam? Okay, so the styrofoam cup is a great insulator, which is why they give you drinks, coffee, or iced beverages in a styrofoam cup, because it doesn't absorb any energy, or if it does, it's minimal. But like beakers and metal objects, they absorb energy like crazy. So we have to account for that, which is going to be related to their heat capacity, the object's heat capacity. So big C, you'll notice this is capital C, not a lowercase c, is the heat capacity of a given object. How does the units differ? How do the units differ? There's no grams, right? So specific heat capacity has grams in it because it's an intensive property. Heat capacity is an extensive or extrinsic property, which means it depends on the mass of the object. So if you have a small styrofoam cup, it's going to absorb a little tiny bit of heat. If you have a huge styrofoam cup, it's going to absorb more heat. The mass matters. So that's what an extensive property or an extrinsic property means. What they usually measure energy release or energy transfer in is something called a bomb calorimeter. They have this at Duke Energy for like combusting coal to see how much energy is in their coal. They have this at like any food plant, so food and drink manufacturing, because they put their Dorito chip in there, they catch that baby on fire, they see how much energy is delivered to the bomb calorimeter, they figure out how much calories are in the Dorito chip. Okay, that's what they do in a manufacturing side of things. So the way they actually use the calculation with the heat capacity is Q of the calorimeter is equal to cat. So C delta T. Notice it's a capital C. How do the units work out? What's the unit for C? What are the units? Joules per degree Celsius. And then delta T's got to be in what? Delta T's got to be in what? Degrees Celsius. So what cancels? So Q is still measured in joules. Okay, we'll pick up with this tomorrow, okay? All right, so homework-wise, I want you guys to make some progress on the problem sets. Just switch to the two problem sets you have on the first page. So, make some more progress on the work energy side of things. You don't have to do all the start ones. You probably just want to get some more practice for yourself. And then you can't do all of the heat transfer side yet. You can do a couple of them. So if you want to do the ones that come forward right now, for the first half. If you already do one, you might be able to do 2 and 3 and 4. So I'm going to do the ones that come forward. We'll finish this up tomorrow, okay? I'll update the website, okay? We didn't quite finish.